Hey, thanks for watching. In this video, Jim Bergmann is speaking at the second annual HVACR Symposium here in beautiful Claremont, Florida, talking about furnace commissioning. This is one of my very favorite talks that Jim gives, and he has a lot of excellent insights on furnace commissioning. I know it's long, but it is Jim Bergmann, so I'm sure you'll get a lot out of it. Big thanks to Jim, all of our sponsors and speakers, especially MeasureQuick and Diversitech for sponsoring the event and making it possible, as well as Emerson for doing the online virtual presentation. The reason we have this video is because of the generosity of all of our speakers and sponsors for making it possible. Again, big thanks to Jim. If you want to find out more about his excellent tool for diagnostics and commissioning, it's called MeasureQuick. Go to MeasureQuick.com. Thanks for watching.
Probably the most important thing, and this is with gas heating, is to take your blinders off and to become a master of the obvious. I don't know if you guys have ever seen horse blinders before, but the whole idea behind horse blinders is everything's gone in their peripheral vision. All they see is straight ahead, right? And that's the whole problem with our industry, is everybody looks straight ahead. We've got what we call appliance fixation. Everybody's fixated on the appliance, right? And they don't look beyond the box to actually see what's wrong. Right? When somebody says, I'm going out to work on a gas furnace, this is literally what a lot of techs think is they're working on a gas furnace. And that's the only thing they see in the basement is the gas furnace. And I was watching Dave Richardson's seminar a little bit this morning, and I'm like, yeah, he gets it. You're not just looking at the gas furnace, because everything interacts with everything. When you're looking at that furnace, it's not just a furnace, it's a system. It's a system, and it's tied to a lot of subsystems in your home, right? I mean, if you look at that, we got a control system, right? We got our thermostat. We got our air distribution system that's taking the furnace and moving the air through the house. We got our air filtration system that's filtering the air. We got our condensate drain system. We got our indoor equipment, our venting system, our makeup air system, right? Then we got components like the heat exchanger on there, the fuel delivery system, right? And so when you start looking at all these subsystems and you start thinking of gas heating as a system instead of, and even the house is the biggest system it interacts with. That's what Dave was talking about this morning, right? When you start looking at that as a system, that's when you're going to really understand how to make gas heating operate safely. And I think it's interesting in our industry when we talk about, everybody's always fixated on heat exchanger, failures and things like that. And it's just like Dave was saying, it's not the heat exchanger that's really the issue in 99% of CO poisonings. It's actually that there's the furnace, if it comes from your furnace at all, which is highly unlikely, if it comes from your furnace at all, it's because it's produced by your furnace and there's a path to get it back into your house, right? And that's what we're talking about here. This is a classic venting system problem, right? You can see on there those rings are warped up, right? People look at this stuff all the time. There's guys that look and go, wow, those rings must be defective, right? Can't believe the manufacturer didn't make them high temperature rings, right? And it's hard to figure out why it's happening on the cold side too. And it's like it's the venting, it's a flue gas spillage that's causing that thing to work. And it's like, just be a master of the obvious, right? Don't be fixated on the furnace, because the furnace is not like the problem. It's everything that's attached to the furnace that you got to look at. It's that when we always talk about, the 80 plus furnace, they go, 80 pluses are great because there's no draft hood anymore. Well, it's hooked to the draft hood on the hot water tank. And you got to look at that, and you got to consider everything that's attached to it, right? So check in for sizing when we're looking at the vent system. And this is crazy stuff because we don't think about it all the time. Too many guys in this industry, they get so fixated on the appliance that they don't look at things like the venting system. Is it the proper size? Is it the proper pitch? Is it the properly supported, PVC pipe? Is it supported every 4 foot? Does it have a proper termination? Bill Spohn and I went out, it's got to be 5 or 6 years ago now, on a CO poisoning. We got called in as expert witnesses for a company up in Cleveland. The lady got CO poisoning, she got brain damage, right? They pulled out a Comfort Maker furnace because the Comfort Maker furnace had a crack in it, right? Maybe a small crack, and they said it was making CO, so they tagged it, shut it off. They come out and they put a brand new Lennox furnace in there. And the Lennox furnace, when they tested it, the technician actually wrote down that it was not working properly. And I think it was producing high CO. And They used a standard of care, what's called a standard of care, and we're going to talk about this a little bit in our industry, but there are documentations in our industry of what would a reasonable person do under that circumstance, right? So if you ever get called into court and you do have something happen to you, they're going to look and say, well, what's the standard of care for your industry? If it's making 17,000 parts per million of CO, what should the technician do, right? And did you do that, right? It's the same thing we do to doctors, right? It's called this is what we're trying to avoid is malpractice, okay? So are you looking at these things when you're there? And what we found was the technician did not shut down that furnace. So he said, hey, cracked heat exchanger, boop, 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 freaking out, got to shut it off, right? Sell our new furnace, puts the new furnace in, making high CO, doesn't shut it off, right? Now the installer came out, they went from a single stage to a two-stage furnace, okay? Lennox and their directions, they have very specific directions. They had a 4-inch flue pipe. The new one had a 4-inch flue pipe. Old one had a 4-inch flue pipe. Perfect, I don't have to spend any time changing the flue pipe. Cuts it off, hooks it up, repipes it in, walks away. On the end of the flue pipe, it was supposed to neck down from 3-inch to 2-inch. Anybody know why we do that? Exhaust accelerator, right? So now the furnace is making, it's a two-stage furnace now. It's running in first stage. It's making 17,000 parts per million of CO. But hey, it's all exhausting outside. But it has no accelerator on there. So guess what it's doing? It's pooling by the house, right? Now, you guys have all seen these fireplaces people build into their homes, and they extend the floor joists out so they can support the fireplace. And then they put, soffit underneath there. Ventilated soffit, insulated, and all kinds of stuff. Well, that extension of underneath the fireplace was actually now a pathway for that CO to go up through that ventilated soffit and back into her house. Now, the other thing they didn't think about was what Steve Rogers was just talking about, which was zonal depressurization, right? You're talking about having a micromanometer in there to actually see what's happening in the basement. So bottom of the furnace has an open base pan on it that nobody screwed down, and they have a pretty restrictive filter. So when the furnace comes on, the base pan's lifting up because nobody screwed the base pan down. So now we're depressurizing the basement. So now not only got a furnace that's making CO, I'm not exhausting the CO away from the house. I've got a path back into the house, and literally all we did was take and you could literally take on this furnace and take a theatrical fogger and shoot it out the house, through the vent motor, and you could watch it pull right back in, right into the house, filling her home with CO, and this lady's got permanent brain damage, okay? And now, you gotta ask yourself, is that the kind of thing that you want to happen? Now, these don't happen very often, but they do happen, and it's because the technician focused on the furnace instead of focusing on the system, right? The odds of a CO poisoning are about the odds of an electrocution, right? So I don't think that they're going to happen. In fact, your car in your garage is more likely to give you a CO poisoning, or your fireplace running in your house and it smoldering out is more likely to give you CO poisoning than your furnace is. But it can happen, and when it does happen, it's usually catastrophic. We've had probably, how many, do you think we had about 12, 14 CO deaths in this year, right? So, yeah, so when we do have them, but on an ice storm, believe it or not, people are killed by their generators, right? They lose their power, they bring a generator in the home, they're using charcoal to try and keep warm, right? It's not the furnace that's killing people, but it can happen. In this case, believe it or not, it was an improperly installed condensate trap, right? The condensate disposal system. Well, how can that happen? Well, air sucking backwards up the condensate drain was not allowing the secondary heat exchanger to drain out. As it filled with water, right, as the secondary filled with water, it couldn't bring secondary air in for complete combustion. Bill Spohn and I sat and watched this thing run. It would fire up. And Jim Davis will tell you, he was probably the first one to make me aware of this, is rising CO, right? He's always real big on rising CO, and I just thought he was a little flaky for a few years till I saw rising CO for the first time, right? And what'll happen is it'll start off at 1 or 2 parts per million, and it's like literally like it goes up a straight wall. It'll hit 30, 40, 50, and then it goes to, maybe 400. And when it hits somewhere around 600, it might go to 14,000 or 17,000 parts per million, because all of a sudden, you get to a point where there's not enough air to support combustion, And we're talking parts per million here, right? I mean, so as soon as you don't have enough air to support combustion, CO goes up to the roof. So that furnace, when the technician was there, it would run fine for about 20 minutes until it got enough water in the secondary heat exchanger to actually start backing up. Once it started backing up, then it started making CO. Now you got a two-stage furnace. Guess what? I have a two-stage furnace in my house. It ran 320 hours last month, which is about 10 hours a day, okay? 30 days, about 10 hours a day, 300 and some hours. That's why that furnace was such a death trap, because it's making high CO and it's running an extremely long time because all those things coming together are what's causing the problem. We all the time, we walk into the furnace room, and Dave was talking again about carbonic acid, and this is also, these are different acids. These are from dryer chemicals and things that happen. When you see corrosion and pitting of heat exchangers like that, that's not because the furnace is a piece of crap. Right? Carrier doesn't make crappy heat exchangers. I see this all the time. These Carrier heat exchangers are horrible. No, the environments that we put them in are horrible, right? So when you have that bounce dryer sheets in there, you have 4 paints, you have solvents in there, you have bleach in there, right? Look at, this is a classic, oops, I shuttered myself here. This is a classic laundry room, right? Again, goes back to what Dave was saying this morning, right? Every 1 CFM in, you got to have a CFM out. I'm going to steal that from you for this presentation, all right? And here we got a dryer that's definitely exhausting CFM out, and we have a wonderful 2-pipe furnace that they did a 1-pipe installation in, right? Why would you do this? I mean, we got a perfect 1 CFM out, and it's engineered solution, and somebody decides to save $7 in fittings and another $20 in pipe, and maybe another $20 in labor to not install that second line on that furnace. And they're pulling in, we're in a laundry room. All those chemicals, all that bleach, all that stuff is now getting pulled into combustion air, and that's what's going to cause problems in the furnace. Right? Again, looking at the venting system, I went out just this year. We see this a lot, right? Vent systems rotting from the inside out. This means that you have chemicals, you have acids in your flue pipe that are eating and attacking the flue pipe and eating it from the inside out. And this, you would never see this unless you walked around the back side of the vent system against the wall where it was touching a brick wall to see that there was not only a cold spot where it caused condensation, but then also corrosion. And people look at this stuff all the time, and they're so fixated on the furnace that they forget to actually look at the appliance. Above, right? I'm at an installation a couple months ago, and we're looking at everything, and B-vent has 1-inch clearance, right? I'm standing there looking. Well, there's a big enough hole there for 1-inch clearance, but when the roofer roofed the pipe, he pulled it against the side, and now the clearance is gone, right? And this becomes, again, a master of the obvious. Here's a lovely chimney liner, right? Did you guys know that part of the fuel and gas code, I think it's maybe Appendix A, requires you to actually disconnect the venting system and look inside the venting system to see if the venting system is intact? There was a pile of aluminum that you could have filled a shop vac with from this chimney liner. It was completely gone, completely disintegrated, because again, acids, uninsulated liner, right? This is very popular in Ohio where we put liners in, we don't insulate them, right? These things happen, and you got to become, again, a master of the obvious, right? Vent terminations. I cannot stress enough to consult the manufacturer's venting tables on sizing, number of elbows, the length, right? It's pretty cool when we're talking about the large vacuum hoses yesterday. When you go to a 3-inch line, it's to reduce friction, right? So as you go to a longer vent system, you have to upsize the pipe so you have less friction in the system, but you may have to neck it back down again. So you minimize all the friction for the long length, but then neck it down again to get the exhaust gases away from your home, right? This is induced draft heat exchanger inspection. It was published by AHRI, okay? At first I thought this was, I looked at the standard, I thought it was a pretty crappy standard, but the more I thought about it, the more I thought, wow, this is actually very significant to our industry because it's one of the only standards for testing heat exchangers. Back in 1989, we had the four-part heat exchanger inspection, which was a flame disturbance. It was visual inspection for cracks. It was using a chemical method to check for CO. And you remember what the fourth one was, Dave? Tracer gas method, yeah, and it was very expensive, and it was also very inaccurate because it picked up almost all heat exchangers leak. Okay, they're not hermetically sealed. If you were to take a heat exchanger and fill it with water, it's gonna drip water out, and that's just part of the way it's designed. In fact, when you guys are picking up cracks on a furnace, and you swap out you're so fixated on the crack, you are completely fixated on the wrong thing. What you need to be fixated on is why did it crack, not that it cracked. Because when you're going to take that new furnace and you're going to put it in on an existing duct system with that existing venting, with those existing registers, and you're going to use the existing size, right? You go, well, it's 100,000. Let's just put another 100,000 back in. It worked fine for the last 4 months, right? And you change it out again, you're not addressing the root cause. Now, what was interesting is this new AHRI heat exchanger inspection, this is what's called a standard of care. This is a document you need to be very aware of. Because if you get involved in a CO poisoning, somebody's gonna come back like a smart guy like me or Bill Spohn, right? Sorry to be conceited, I don't mean to be, but I'm the guy they're gonna call, and I'm gonna just say, hey, are you aware of the 2008 guideline? I think it's 2008. I don't have my glasses on here for reduced draft heat exchanger inspection. And you're going to look at me, you're going to go, no. I'm going to say, really? So how did you test the heat exchanger, right? Or how did you test the system? Because this is a guideline for all furnaces that have induced draft appliances. So you're going to be expected to, did you watch for flame disturbances, right? Did you measure CO in the Airstream, both supply and return? Did you measure CO in the stack? Did you verify the installation was correct, right? Did you get the owner's manual out and look at the venting requirements for that appliance? Did you physically inspect the heat exchanger if all these other systems failed, okay? And this is extremely important. 4.1 of that guide, look for flame disturbances. 4.2, measure CO levels. 4.3, measure CO levels in the stack. 4.4, verify proper installation. 4.5, visually inspect the heat exchanger by removal if you can't see the damage from the inside. You can just go right online and pull this inspection down, right? So if you're working in this industry today, you can do it on a cheap like Nate does with a multimeter, or you can be a real man and buy a combustion analyzer and actually have much more fun in this industry, because who doesn't want to play with fire, right? It's much better than electricity is. Right, Nate? Yeah, he's smacking his head. So number one, I do a lot of work with AccuTools and the combustion. I don't care what combustion analyzer you buy. Just please, if you work on gas appliances, own one. Because now you're aware that there's a standard that you really need to have one. All analyzers, whether you're talking Testo, Bacharach, Blue Flame, they're all basically the same. Okay, they're gonna have 3 cells in them. They have 2 cells, 3 if you're in California. They have an O2 cell, a CO cell, and they have a draft gauge built in, and they have temperature. Right. So there's 4 measurements a combustion analyzer makes. They all basically do exactly the same thing. And what they do is they keep you out of harm's way, and they keep your customers out of harm's way, okay? You've got to have one if you're going to work on gas appliances. The first thing you want to do with a combustion analyzer, ambient CO, and people don't realize this is not just for combustion analysis, first of all. Okay, that's what I thought when I first bought this tool. I'm thinking, oh, it's just a combustion analyzer. It's got one function, it's measure combustion. It's actually got an ambient CO testing. So you can walk to the home, you can test the ambient air for CO, which is something that you should do before you do any testing. You can use it for setting your incoming gas pressure, you can use it for setting your manifold pressure, you can use it for doing your temperature rise, you can use it for total external static pressure, you can use it for pressure drop across filters, you can use it for combustion testing, your furnace, your hot water, your stove, your dryer. You can use it for CAS testing and draft testing in some cases, depending on the accuracy and resolution of the manometer. After using the Tech's new manometer, I think it's the 8, I can't remember the exact model number, DG8. If you don't own one of those, I'd highly suggest you look at one of those, because that is one slick instrument because it constantly auto zeros, right? When you have a high accuracy, high resolution manometer, they tend to drift. So the one in your combustion analyzer is good for short-term testing. What Dave was showing you earlier with the Dwyer 760 air meters, that's the number for that, right? Yeah, Dwyer draft gauge. I think they call it a 760 air meters, the full name for it. But that is probably one of the best visual indicators for continuous measurement of draft. I've used one of those things for years. In fact, I think I met Jim Davis at a supply house at a Moral Control in Akron. And he looks exactly the same today as he did back in 1989. He has not changed, exactly the same. Am I wrong? Yeah, he is like Dick Clark. All right, so let's talk a little bit about ambient CO testing. Ambient CO can be checked and recorded with a combustion analyzer. It should be, I highly recommend you carry a personal CO meter with you, whether it's a Testo, Sensit. They will save you from CO exposure at some point. I'm not going to say they're going to save your life, but they'll definitely save you from a migraine, okay? They'll definitely save you from a flu-like symptoms. They'll definitely, and especially like here in Florida, you go, huh, who would need a CO tester here? Well, guess what? My house that we're in has got a lovely pool heater, right? Powered by natural gas. Pool heaters are notorious for making CO, especially when they put them in a small room and attach them to the house, so they have a pathway for getting CO into the home, right? So you need to make sure, no matter what climate zone you're in, no matter where you're at. I have had CO meters go off in my van when I'm driving a van because I had exhaust leaking into the van. And a CO meter, here's the whole thing. Unless you're aware of what the problem is, unless you've made a measurement, unless you know, you can't make any corrective action. And that's the whole thing that it kills me with our industry, is we have people that don't measure everything. You need to measure so you can at least know when you have a problem. All right? Typical alarm levels are 35 to 50 ppm, and a typical stop work is around 75 ppm or higher is on there. You want to zero your analyzer in fresh air, okay? All these analyzers make a relative measurement. So if we're like in New York City, and it's middle of the day, it's going to be 6 ppm of CO in the ambient air. If you were to go to upstate New York, zero your CO analyzer and drive down back to New York City, you'd be reading 6 ppm in the air, right? That's a baseline CO. What we're concerned about is CO above the baseline. So we always need to make sure that we're zeroing the analyzer in fresh air, and we test in the ambient air, that you're walking around and you're testing about chest level, and you should test on every floor. Because, again, stack effect in homes, we don't want to just test in the basement next to the furnace. And there's other possible sources of CO we'll talk about in a minute. Next thing you want to do is you want to test in the Airstream. Now, how many of you guys are staying out here in like a Airbnb house where you're here, or staying in a home? How many of you guys have noticed where they put the furnace at? In the garage, right? They put them in the garage. Now, guess what the garage is a major source of? It's a major source of CO. People back their cars in their garages. People start their cars in their garages. And luckily here in Florida, they don't warm them up too often in their garages. But if you start your car in the garage and you back out and you close the garage door, and we had any wind blowing towards the garage, you can guarantee you've got a garage full of chemicals in there that are going to end up in your furnace through duct leakage and through the return air leakage in the appliance. So you want to make sure you're testing in the Airstream. You want to test in the supply and test in the return, okay? You want to test also for CO levels in the stack. Now, the standard that AHRI has in there is 200 ppm or less. We typically strive for 100 ppm or less, and there's typically no reason you actually can't get an appliance down to 0. We actually provide excess air to an appliance so that it doesn't produce CO. Okay, over 100 ppm, under 100 ppm is advisable. Over 400 ppm, I'd advise you to lock the appliance out, right? And this is all measured CO air free. So here's, because we're in Florida, and all you guys can understand this, okay? It's, dilution is, if you had your kid pee in the pool, right? He had a bottle of pee there, and he dumped it into he had a bottle. There's so much pee in the bottle, right? It's one quart of, now we dumped that in the pool. The amount of pee didn't change. We just diluted it, right? Nobody wants to go swimming in that pool. Once you dump that pee in there, I guarantee you nobody will go in the pool. And it's the same thing here. When we're making a measurement, we want to know how much pee is in the pool, right? So that's what CO air free is. It's just simply how much pee is in the pool. We can tell you exactly because we're taking out the effect of dilution. So if we know how much water's in the pool and we can measure the P in ppm, we can tell you, okay, here's the CO or the P, here's the pool P free, right? And that's what we're trying to do is we're just trying to take out the effect of dilution, right, on there. So when you want to know how much, because the furnace, if we just said, hey, it's making high CO, just keep adding dilution air, right? That's what we would do, is just keep adding dilution air. It would look like there's less and less and less. But in fact, if we want an apples-to-apples measurement, we have to make a CO air free. Characteristics of carbon monoxide, it's obviously colorless, odorless, tasteless, mixes well in the air. It really doesn't stratify. It does follow convective air currents in there, and it's obviously highly poisonous. If we get exposed to it, it's going to get persistent headaches, dizziness, fatigue, right? You can have long-term damage from that. There are guidelines for health exposure. So the 9 parts per million in the US is the maximum 8-hour exposure limit that we want to see, and there's all kinds you can reference on there. But again, when you walk in that, you can't just focus on the furnace. There are so many other sources of CO that are not the furnace, and that's most likely your true source of CO. It's going to be your stove. It's going to be your gas log fireplace. It's going to be your dryer. It's going to be the auto that's running in the car, right? It's going to be believe it or not, I think the thing that I've seen produce the most CO consistently in a home is the hot water tank. The hot water tank is a large enough appliance. It's usually around 50,000 BTUs. It runs a lot, depending on your household. Look at Brian Orr. Brian Orr has 10 kids. I don't think his hot water tank would ever shut off. It's got to run continuously, right? How do you have a family that big? He's probably got, I'm sure he uses a heat pump hot water tank because he's not a real man. But if he used a gas hot water heater, right, he would have a pretty potential large source of flue gas in his house, right? So don't get fixated on the furnace. That's the big takeaway here. Draft and spillage, right? Most people don't understand what the actual function of the draft hood was. The draft hood was actually designed to prevent fires, right? Because anybody ever see the movie Backdraft? Right? So what happens if we can't get air in and the fire starts to smolder and we open it up, it's going to fly out the front. The flame is going to look for oxygen. It's always going to look for air. And the draft hood separates the appliance from the draft. So it goes back to what Dave was saying earlier. What's the most powerful force? It's the convective heat that's rising up to the appliance. And what's cool is this process called entrainment. So it's going to pull, as the air rises up, it's actually going to pull air in behind it to replace it. It goes back to the 1 CFM in is 1 CFM out. And what's cool with natural draft is if they design the appliance perfectly, and the design of the heat exchanger is going to control the airflow through the heat exchanger at the precise rate that they get the exact fuel and air mixture. In fact, if you look at a lot of natural draft appliances, they'll run around 20% excess air. I always thought when I first started at this that the natural draft appliances would be running really, really high excess air levels. And in fact, they typically run very low excess air levels because they can so carefully control the draft. So it's the design here is it separates. If you look at that drawing I have up there, it physically is separating the appliance from the draft, and it keeps the burner, it keeps the heat exchanger, the air from being drawn too quickly through the firebox. Because it's physically separated. Have you ever bought a straw at Sonic, right? And you go to drink your shake and it's got a little crack in it, and you can't get anything up the straw because air takes the path of least resistance, so it's going to go through the crack in the straw much easier than it's going to pull through the to the heat exchanger. When we separate the appliance from the draft, right, that's what's going to happen. So it's going to pull in the air at exactly the right rate as the flue gases rise to the heat exchanger, and you're going to get the amount of primary and secondary. Primary air always goes through your burner. Secondary air goes around the heat exchanger package. We need both. And if you were to take, for example, and you put a bird in the flue, right, and what's going to happen is we're going to get spillage. Now, what's cool with this is on a natural draft appliance is if it's burning properly, it's going to emit carbon dioxide, water vapor, and heat, right? Now, the reason that we don't, you guys think about it in Ohio, we're pretty crazy, almost as bad as Kentucky, but not quite. We don't marry our cousins. So, but we have non-vented appliances in our homes. So we have space heaters we put on our front porch, and we just burn gas just in the open air. It's really cool, right? No venting on them, and people have used them for years. I think we're starting to see fewer and fewer of them. Blue flame heaters, infrared heaters, all kinds of different heaters. And so as they're burning this gas in here, if it's burning right, all it emits is carbon dioxide, water vapor, and heat. And the reason we don't vent large appliances like that in our home is because of the tremendous amount of water vapor that they make. Now in this case here, when we block that chimney with a bird in there, what's happening is because that draft hood is separating the appliance from the draft, it's not going to create a fire, right? This is why if you do modify a draft hood and you were to cap it off, you'd need to have a spill switch so that you could shut the appliance off so when the fire comes out the front, you're not going to cause a problem. So when we get that spillage in there, it's going to be simply carbon dioxide, water vapor, and heat. Now that's if everything's working correctly. In a lot of cases, we also have that unburned fuel, right? And if we have a recirculation of flue gas, this is where it primarily happens, we're also going to get that carbon monoxide. But you can have an appliance spilling in your home. I've seen literally appliances spilling in your home for years. And what's crazy is the hot water tank's over here spilling continuously, and this guy is going, there's a microscopic crack in your heat exchanger. Your whole family's going to die. And he's tearing out the furnace and putting in a new furnace, and he didn't fix a single problem in that home except for the cracked heat exchanger, and he completely fixated on the furnace, missed the hot water tank. And this goes back to you've got to think systems when you're looking at these appliances, or you're going to create problems. And it goes back to, there's been guys, I bust Nate's chops all the time, but he's made me aware of things on the blower door side. In his quest to actually make electric work in homes, right? He had to eliminate all of that lovely infiltration air that we get to actually make that thing work. Yeah, he thought the house, it does have to breathe. But there's two things we want to talk about. One is infiltration, one is ventilation. And by the way, it's very important to understand the difference. Ventilation is controlled with a fan. Infiltration is not, right? And so we want to eliminate infiltration because we can't control it, and it doesn't always do what we want it to do, right? That's what Dave was saying this morning. But if we always use a fan, we can control it precisely, all right? So the draft hood must establish draft within 5 minutes. Now, when you start an appliance, it can have a cold chimney, but once that is warm, it should stay warm. And I think one thing that I'd like to clarify, I was listening to Dave's presentation, which I thought was excellent, by the way. What we're concerned with is the air has a very low specific heat value. It takes a very small number of BTUs to take the heat from the flue gases and cool them back down. And there's two things we want to be concerned with. The reason we want to have a warm stack is not primarily the draft, but it's more the condensation, right? We don't want to condense inside there. But once we get that stack warm, it's going to tend to stay warm. But there are standards for draft, and it must establish draft within 5 minutes. You've got to make sure you're checking all the way across. Whenever you look at a furnace, if it shows any evidence of rust on the draft hood, something's wrong. That appliance most likely needs replaced. And in fact, today I tell you, if you have a natural draft appliance, it probably needs replaced. They're just to a point where we don't need them in homes anymore, right? Induced draft and 90-plus furnaces with steel combustion are really the way to go. We still have things like boilers that are going to be natural draft. I'm sure you can still buy them out there, but they're things that I would avoid. Oops, I blanked myself again. All right, so we typically use a wind pencil or smoke indicator. Look for evidence of rusting, dangerous spillage, right? Do not ignore the hot water tank. That's most likely your source of CO because a homeowner went down to Home Depot and they bought themselves a hot water tank and they put it in and they torqued the burner when they were putting it in and it's impinging on the bottom and it's making massive amounts of CO. And you got to make sure that you're testing that. Again, same way all the way around the hood. Whenever you see those melted plugs like I showed you in an earlier sign, that's not an indication of cheap plugs. That's an indication of spillage, right? And that needs to be addressed. If you walk in any home that's got a gas appliance, you need to look at all the appliances in the house. When I was a high school teacher, one of the things I used to do is I would have my students go out, and I had a furnace and a hot water tank that were common vented like this, right? I'd give my kids a combustion analyzer, I'd give them everything and hook it all up. And being kids, you know, they'd measure the draft and it would read them wrong, it would read positive instead of negative. So they just they'd fix the problem real quick by just putting the hose on the other port. Because of course it can't be positive pressure in the stack, it's always negative. So they just move the hose over and get a negative reading on their combustion analyzer. And they come back and they say, yeah, Bergmann, everything's right, clocked the meter, got this, and got this. And I said, super, let's come over here. You just killed your customer. What? No, you just killed your customer. How could I kill my customer? I walk over and I just had a damper in the flue pipe, it just closed off. And the top of the hot water tank's wet and it's hot, the plugs are melted. I said, you did two things wrong. Number one is you did not, when you got a screwy reading on your draft gauge, you didn't take a look and see what was causing that. You didn't use a smoke pencil to verify, is it blowing in or sucking out, right? Visual, there is nothing that beats visual inspection. Use your eyes, use your senses. Your instruments will fool you, and you have to, when you get fooled by your instruments, take the next step and do something simple like light a lighter in front of the flue pipe and see if those gases are sucking in or sucking out. Get a smoke pencil, is it sucking in or sucking out? Do something simple to verify what's going on before you dismiss it. We dismiss way too many things. Don't tell me you guys haven't seen something in your career where you look at something and it intrigues you, but you're so busy with everything else that you got to do, and your dispatcher's calling you and everybody else, and you get home, and about 3 o'clock in the morning, you wake up and you start thinking about what was causing that problem, right? And you're sort of in that twilight of sleep, and you go back to bed and you wonder, you know, what the hell did you just leave that you should have seen? And it happens to all of us, so you just gotta slow down and make sure you're doing that right. Any questions up to this point, by the way? All right, so common venting is a huge problem. Setting the manifold pressure on an appliance, all right? One of the things that and I don't know if I got the slide in order, Brian had to ship these to him a week ahead of time, so hopefully I got this in order here. But setting your manifold pressure is not the key. Everybody wants to say, I'm going to set it at 3.5 inches. There's actually an acceptable range of manifolds. 10 minutes? 10 minutes for what? You're going to take a break? So, all right. Now I got to talk fast. All right, how much air is required? The key thing is that for every cubic foot of natural gas, there's 10 foot of air required. All right, additional 5 cubic foot of excess air and 15 foot of dilution air if you have a draft hood on there. So you need 15 to 30 cubic feet of air. What people don't often tell you is that natural gas comes with different heat contents. So and they're pretty consistent for your region, but you have to set it for your region. And these are average heat content, meaning the heat content's gonna go up and the heat content's gonna go down. If you went to CSA labs, they actually track the heat content and it'll go from 900 BTUs to 1050 BTUs in a day. But the average heat content is X. And they tell you the average heat content because we supply this really cool thing to a furnace called excess air. So we supply it with enough air that as the heat content changes, we have enough excess air to assure complete combustion. The key thing here is that when you're setting the manifold pressure, there's a range of manifold pressures from about 3.2 to 3.8 inches. Now, you're going, I've never seen that in a manual in my entire life. The manufacturer has 3.5 stamped on there. Well, what you need to do is actually research, go to Carrier's website and research converting an appliance from propane to natural gas. And for some odd reason in there, they tell you there's a range of gas pressures that are acceptable and you want to clock the meter, right? So we're gonna, and here's what we typically do is I'll set the meter at 3.5 inches of pressure, and then what I'll do is I'll go out and I'll clock the meter. And I'll see if that fuel pressure has to go up or down to get the fuel pressure correctly. So these charts that you're looking at, notice this clock the meter chart here, these charts that you're looking at are all based upon a heat content of 1,000 BTUs per cubic foot of gas. You may be in an area with 950, you may be in an area with 1075, and you're gonna have to adjust that. And after you get once you clock the meter, if you need the fuel pressure below 3.2 or above 3.8, right, then you're gonna have to change the orifices if required. Now everybody's going, oh, you're modifying the furnace. Well, guess what? If you read the dang directions, right, it'll tell you right in there that you can change the orifices in the appliance. Now, I'm not a big advocate of drilling orifices. Some guys like to drill the orifices. They're a little tricky to drill straight. Not a big advocate of that, and you have to have what's called a burnishing tool. It's a science, and some people, they'll do it, but I'm just telling you, don't go out to Harbor Freight and buy a numbered drill set and decide you're gonna use your hand drill and try and drill orifices. Ain't gonna work, you're gonna have problems, right? And then it's much better to just go to the manufacturer and ask them for the right orifices. And guess what? We're in a place in Florida where these guys have been changing orifices their entire career. They convert appliances from natural gas to propane, right? Every single furnace out there you can convert over to propane with a propane kit. There's no reason we can't adjust an orifice on there. Supplier, this is just a little chart on calculating the input based upon different heat contents on there, because Caleb's going to throw me off the stage because I talk too long, blah, blah, blah. MeasureQuick, we actually will do this for you. So when you you put the fuel pressure in, you clock the meter, it'll tell you whether you need to upsize the orifice, downsize the orifice, or where you need to set your fuel pressure. It does all the math for you automatically. All right, yes, sir. Altitude comes into play as far as primarily your meter. There can be, and you do have to derate your appliance because the O2 content drops in the air. There's two things you got to look at: temperature compensated meter. I was get confusing myself for just a second, which happens periodically at my age. So when you're talking about altitude, right, what we're talking about is, and again, your gas appliance will tell you in the directions that you need to derate it for the altitude. It's because the density of the air changes. One of the most important things people need to understand is we don't move cubic feet of air, we move pounds of air. Everything we do is mass flow rate. 100% mass flow rate, that is one of the most important concepts to understand. So we're talking about air conditioning, right? And a cubic foot of air weighs 0.075 pounds per cubic foot times 400, that's 30 pounds per minute per ton. So a 5-ton air conditioner is moving 150 pounds of air a minute, right? So if you could take that air and crush it into a tank, it's 150 pounds. When we go up to altitude now, and the density drops down, that 150 pounds might go to 100 pounds. So now we got to take that airflow from 400 up to 450 or 575 to get the same amount of air across the heat exchanger. And then we also have to derate the appliance because the air densities drop down because we don't have enough oxygen to support complete combustion. And those get into some pretty complex things that you need to talk to your manufacturer about. But this, again, when people get CO poisoning, 5 minutes, go away, all right? So these things are things you need to take into account. So temperature testing, right? Once we get the manifold pressure, the input correct, right? Manifold pressure within the acceptable range. This is one of the most important steps by far, is making sure we have the correct airflow across the heat exchanger, right? Now, I always recommend closest supply register and return near the furnace. I see guys all the time drilling holes in the ductwork and putting the probe above. That is completely the wrong spot to measure your temperature rise. Get 6 to 10 feet away from the furnace where the air has time to turn and mix on there. And if you're going a Y branch, you may want to use even 2 Supplier probes. MeasureQuick will allow you to use 2 wireless probes that will average the temperature on there, because sometimes you'll get convective air currents taking heat one way or more the other, and you might have to get a second measurement to get an accurate measurement. You want to be out of line of sight of the heat exchanger. You want to allow that to stabilize. So the important thing to remember when we're talking about steady state, which Jim Davis will tell you he's never seen steady state, I've seen it, right? And steady state just means that, and here's what you got to understand is your stack temperature is going to continually rise because your return air temperature is continually rising. So stack temperature is going to never stabilize. It's going to creep up as return air temperature creeps up. What we're looking for is stabilization of the delta T across the heat exchanger, right? So when it stabilizes at 40, that's what we consider steady state. What Jim's always talking about is steady state of combustion, and that combustion is always changing because the dynamics are always changing and nothing's ever stable. And he's correct about that. But when it comes to a temperature rise, we can actually tell when it's stable. Worst case draft testing on here, it's not the furnace we need to be concerned with. It's the dang hot water tank. And you look here, this is my basement. I'm standing there, and behind me is a door. And when I open up that door that's right there, guess what? It covers up the hot water tank, right? And in that room is a dryer. I have like the worst combustion air zone you can have known to man because I've got a dryer in there, I've got a small room in there, I had provisions for combustion air in there. But it's the hot water tank that's the draft hooded appliance that we have to test. That's the danger in that room. It's not the 90 plus furnace that is vented in and vented out that's necessarily going to cause the problem in the home. Combustion testing, right? And we have the whole combustion guide, you can do this, but the whole idea behind this is we're getting the correct amount of fuel, the correct amount of air, and that's going to give us the optimal combustion on there. This is what we're looking for. You notice that purple line there, the stack temperature continuously increasing. This is what we're looking for right here, right? So the O2 got stable. Look at that CO. It went down, it lit, and it went right down to 0. Our efficiency's stable, everything's stable. This is what it looks like when we don't have stable combustion. And this is what happens when we have issues in our combustion air zone. This was actually an apartment building, an AMHA building, that an elevator was causing depressurization. As it went up, it was acting like a giant plunger in the room. When it went all the way to the top floor, it sucked all the air out of the boiler room. And as soon as it sucked the air out of the boiler room, it all of a sudden hit a threshold where it went from 0 parts per million to CO up to, I want to say it's 3,500 ppm, right? This is, when you're looking at a combustion analyzer and you're looking at things stable, this is the exact reason that Nate said he likes pictures instead of data. Because when you're looking at a combustion analyzer, it spits so much data that you don't see the big picture. And trending is probably one of the most powerful things we've done on instrumentation in a long time, right? MeasureQuick gas heating, it'll do all these types of things for you. And then there's a whole bunch of specific testing of compliance, because I know that Caleb's over there with his finger right over the mic. He's just going to shut me off at my end of time.
I was just informed that lunch food has not yet arrived, so you feel free to go back.
Oh, you sure?
Yes. I'll let you know. I'll yell at you. No, there is a question going back to the CAS testing, though. There was a couple of questions online about what type of manometer you would recommend. People have a lot of the field piece job link probes, and we need to probably clarify what type of manometer you would suggest.
Tony did an awesome job with the job link probes. They are probably one of the most stable probes that I've seen when it comes to static pressure testing, but it's not the right probe for CAS testing. There's two things we need is range and resolution. And if you want the proper gauge for that is actually the DG8 or a blower door. DG8's about a $500 draft gauge, right? And it's expensive, but it constantly re-zeros, and it's going to give you the accuracy and the resolution and the repeatability that you need to start solving some of these building science problems. So that's about the only gauge. I mean, I would not. Testo's got draft gauges built into their combustion analyzers, blue flame back rack. They're all high accuracy gauges, but they don't take good long-term measurements. And for a lot of the work that we do, we can't rely on that gauge not to drift enough over time. We've tried pushing the field piece gauges out an extra decimal place. As long as they're kept at a reasonable temperature, you don't change temperature dramatically, they'll hold the 0, and they probably hold 0 better than anything out there in the market. They're by far, for a low-cost manometer, they got it licked right now. I think they're really good, but it's not a draft gauge. Any other questions, Caleb?
Nope, not right now. I think there's a question over here by
yes, sir.
Nate.
So, relating to the pressures there, how many pascals do you need for draft testing versus external static pressure? That might be helpful.
Yeah, so, well, we don't even measure external static, and there's 28 inches per, there's 28, 28 inches of water column per PSI. And anybody know how many pascals per PSI? It escapes me. 250 pascals to, yeah, so a pascal is about like a gnat fart, right? It's a very, very small amount of pressure, okay? So if you get a gnat, you can capture them, and you hold them up to your face, you might feel a little, that's a pascal, roughly, okay? So you need a very, very accurate gauge. It's actually, again, it goes back to, there's three terms that often get confused. There's accuracy, resolution, or accuracy, accuracy, resolution, and precision, okay? So we're talking about accuracy, that's an absolute thing. It's how close is to the actual measure. So it's against a reference Pascal, right? And then there's resolution, which is how much change can we resolve? And then there's precision, which is how often can we hit the same spot. So you can be very precise, and you can throw at a dartboard. You can hit the same spot on a dartboard every time, but not be accurate. If you're trying to get to the bullseye, you're missing the bullseye, but you're hitting the same wrong spot every time. You're very precise. Or you can be precise and inaccurate, or accurate and imprecise. There's all kinds of ways of looking at that, but you got to get the right tool for the right job. And sadly, good tools cost money. But the thing is that if you have the right tool, they'll actually identify problems that you would otherwise overlook, right? Any other questions? I saw one other arm up there. Yes, sir. So caulking propane, what I've done in the past is just go out and buy a sublet meter. And you can pipe it right in the basement and pipe it into the furnace, out of the furnace, and caulk the meter and set up the propane. Propane can be a nightmare. And I honestly would not set up a propane appliance without caulking the meter, because you can't tell if you've got the right orifices in place and they're the right size unless you caulk the meter. There's just no way of telling. And that's why people have these nightmare stories with propane where they're sooted up and all this other stuff. I followed everything perfect. I set the gas pressure, but you didn't check the input. So the best thing to do is just disconnect the propane, put a meter in line, caulk the meter, pull the meter back out, and you're good to go. And you can order sublet meters for natural gas, and you can order sublet meters for propane. They are different. So you got to get one calibrated for the gas. But if I get I've been in buildings where I can't isolate an appliance, like a big industrial hot water tank or something like that, and all I did is just put a sublet meter in line and caulked it, made sure it was running correctly. Any other questions?
I've got one.
Yes, sir.
So let's say we're on a commercial building, and let's say it's a rental facility, and you have multiple vendors in the building. You can't clock the meter because you've got multiple appliances.
Were you here just a second ago?
Yes.
No, I just said yes.
Well,
go ahead.
The sublet meter would then work for that application too, not just
Correct.
for propane, but also for that application.
That's exactly right. If I want to isolate an appliance where I want to be at the appliance and clock the meter, that's the cheapest, easiest way to do that. Sublet meters are, I don't know, they're probably under $100, and you can get one for propane, you can get one for natural gas. You can clock the meter. Now they are different. They're different sizes, so you got to make sure you have a big enough one for what you're measuring. But for the most part, that type of a meter will work great for that kind of an application. Input is the key to safe gas appliance operation. But don't let the big reason Nate and I argue all the time is because we just like to argue. But the other reason is gas appliances can't be turned down. If you went to Nate's presentation, the challenge we have with gas appliances is they don't come small enough for the actual heat loads that Nate's calculating on a house. It's not that gas is more safe or electric's more safe. It's literally what we're talking about is comfort at this point. And Nate, he thinks you can be more comfortable with a electric appliance because he's never experienced a good quality gas installation. So. No, I do not.
Then you're making an emotional call rather than
yeah. Well, I had a heat pump once, and I wasn't happy with it. So, but I actually do have the Bosch inverter unit in my garage. It's going to go in, and I'm going to test it just to. But I'm not wearing that stupid shirt, so you can forget it. But we are learning a lot with each other, and I'll wrap it up so you guys can go eat. So appreciate you coming out and listening for a few minutes. And if you got any questions or anything, please feel free to ask me. I'm an open book. If anybody would like a copy of that PowerPoint, I'd be glad to share it with you. I'm into educating the industry. So if you want to take it back to your classroom or whatever, you're welcome to have anything I've got. All right?
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to HVACRschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.